Hello everyone, welcome to the channel Top Gate. In this video, I will discuss the semaphore variables. So if you go back to a few of my previous lectures, the major topic that we were discussing was process synchronization. So in process synchronization, we have seen what is a critical section, we have seen what is the critical section problem, also we have seen the solution to the critical section problem. We know that in order to solve the critical section problem, it should satisfy the three requirements. The requirement of mutual exclusion, the progress, and the bounded weighting. So in my very previous lecture, I discussed about the Peterson's solution. The Peterson solution was capable of solving the critical section problem, but it was only able to satisfy the two mandatory requirements of the critical section problem, that is the requirement of mutual exclusion and the progress. It was not able to satisfy the bounded weighting requirement of the critical section problem. Now, what is the problem with that Peterson solution? The major problem with that Peterson solution was that it was only able to solve the critical section problem involving two number of processes. That is, if there are more than two processes in the system, the Peterson solution won't work. Okay, but we all know that we work on systems which are multi-programming. That is, in the system there are several programs, several processes running simultaneously, and there is a possibility that all those programs, all those processes share the same critical region. So if there are n number of processes which are sharing the same critical region, then the problem of critical section arises. So this semaphore variable is actually a solution which is capable of solving the critical section problem involving n number of processes. So we'll see that what is a semaphore variable first, and then we'll see that how the semaphore variable will solve the critical section problem and how many requirements will it satisfy for the critical section problem. Now let's see that a semaphore variable is an integer variable that, apart from initialization, is accessed only through two standard atomic operations, wait and signal, or sometimes we also call this wait as P, signal as V. So it is saying that first thing, the semaphore variable is an integer variable. So it is an integer variable, and second thing, it is saying that it can be initialized, as well as this semaphore variable can be accessed only through two standard atomic operations. Now why do we call this atomic operations? So if you see the literal meaning of this atomic, this means indivisible, something which cannot be divided. Here, this atomic means that, suppose if there are two statements in an operation. So if we say that the operation is atomic, that means both of these statements should be executed when we say that the operation is complete. The operation will only be completed if both of the statements of that operation are completed. That means atomic. Clear? So we have these two operations here, the wait operation and the signal operation. So let's suppose the semaphore variable that we have is S, and on this S, the wait operation is performed. So wait operation is saying that while S is less than equal to 0. What does that mean? We all know that whenever we execute a while statement, how this while loop actually works. So for a while loop, what we have a condition. We check the condition. If the condition is true, what we do? We execute one statement. Again, we go back, we again check the statement. If the condition is again true, we again execute the statement. We again go back, check the condition. If the condition is again true, we again go and execute the statement. So this cycle will go on and on, unless and until we find that the condition is false. As soon as the condition is false, we exit the while loop and we go out. Okay. Now here, if you see that in a while loop, I have put a semicolon here. What does that mean? I have given the condition, but there is no statement to be executed. So that means this will work like this. We have a condition for the while loop, but there is no statement. So this will work like this. So we have a condition, we check the condition. If it is true, we again check the condition. If it is true, we again check the condition, and so on and on and on. So this will actually work like a trap. Will not be able to proceed further. That means the control will not be able to come to this S is equal to S minus 1 unless and until it finds the condition of the while loop as false. If it is true, it will be stuck there in the while loop. It will be continue to skip only. And then the signal operation, in signal what we do, whatever value we have decremented here, in signal operation we will increment that value. So we did s minus 1 here. In signal what we'll do s plus 1. So this is the structure of the wait and the signal operations. Now we'll see that how this semaphore variable will be used to solve the critical section problem. So for a critical section problem, we have three requirements: the requirement of mutual exclusion, the requirement of progress, and the requirement of bounded waiting. So we'll see one by one that all those three conditions are satisfied or not. Now suppose we have say n number of processes participating in the system, and all those processes are sharing the same critical region. So we have, suppose, P1, P2, P3, P4 up to Pn process, okay, who are participating in a system, and they all are sharing the same critical region. So we'll see that for all these processes, if we follow the semaphore variable thing, we will be able to solve the critical section problem. We'll be able to satisfy all these three requirements or not. We'll check all those things. So let's suppose we have a semaphore variable. We take a semaphore variable as s, and then second thing is we initialize this value as 1. So we have a semaphore variable s, and we initialize this value as 1, because the definition is saying that the semaphore variable can be initialized. So we initialize with the value 1. Now remember one thing, this initialization with the value 1 is very important here. That is, whenever we are solving a critical section problem, we always initialize this value as 1. We can initialize with any value, but specifically for solving the critical section problem, we initialize this value as 1. So we have semaphore variable s, we initialize this value as 1. Now what is the typical structure of the process Pi looks like? So every process who wants to go to the critical section will follow this approach. Okay, I'm writing the structure of the process Pi. So every process who wants to go to the critical section will follow this approach. So the process Pi will write, first thing, it will write wait s. It says that, the definition says that the wait operation can access this semaphore variable. So Pi wait s, and then it will write critical section, then it will write signal s, and then the remainder section. So if you see this one, this is your entry section, this is your critical section, entry section, critical section, that is your exit section, and then the remainder section. This is your entry section, and this is your exit section, critical section, and the remainder section. So every process who wants to go to the critical section must execute these statements. Okay, let's suppose P1 wants to go to the critical section right now. So P1 will execute wait s. Wait s means while s is less than equal to 0. So what is the value of s right now? The value of s is 1. So it will execute while s less than equal to 0. That means it finds the value of s as 1, which is not either equal to or less than 0, it is more than 0. Therefore the condition becomes false, hence the while loop is broken, and it will come to this one, s is equal to s minus 1. That is, the new value of s will be now 0. Initially it was 1. Now process Pi, say P1 will decrement the value, and the new value of s becomes 0 now. After setting the value of s as 0, this Pi will go to the critical section. Now it is working in the critical section. Now suppose process P1 is working in the critical section and process P2 comes. P2 again will execute the same thing. It will write wait s. Wait s means while s is less than equal to 0. So s is equal to 0 right now, because process P1 has already done the value of s from 1 to 0. So P2 finds that the value of s is equal to 0. Therefore, it will not be able to go to this statement here. It will be stuck in the while loop. Continuously, it will check that the value of s is equal to 0. So it will be stuck here in the while loop. It will not be able to go to the next statement that we have here. So process P2 will be stuck in this part only. It will not be able to go to the critical section till process P1, who was working in the critical section, now comes out of the critical section, and here in the exit section it will write signal s. Signal s means s is equal to s plus 1. That means initially the value was 0, This 0 was done by P1 only. Now it will write the value as 1. So the new value of S is equal to 1. Now process P2, who was stuck here in the while loop, in the wait operation, it will find that the condition is false now. That is, now the value of S is more than 0. Therefore, the while loop will be broken and it will go to the next statement, S is equal to S minus 1. And the new value will be again set to 0. After setting the value to 0, it will go to the critical section and execute and do its work in the critical section. Finally, it will complete its work and come out of the critical section. In the exit section, it will write signal S, where the new value will again be set to 1 and it will go out and complete its work. So it is very clear here that any process which comes here, either P1 or P2 or P3, the only work that you have to do is first you set the value of S is equal to S minus 1, and then that is from 1 to 0, and then go to the critical section, come out, increment the value by 1, that is again do it 1 and complete your work. So every process who has to go to the critical section will has to execute these statements. So therefore, we can say that if any process is working in the critical section, at that time no other process will be able to go to the critical section. Why? Because the process who went to the critical section will actually set the value of S from 1 to 0, and any other process who wants to go to the critical section will first check what is the value of S. If it finds that the value of S is 0, it will be stuck in the while loop. So all the processes who are actually trying to go to the critical section, they will check in the while loop that what is the value of S. If they find the value of S is equal to 0, they will be stuck there. They will not be able to execute the second statement of the wait operation, and therefore they won't be able to go to the critical section. They only will be able to go to the critical section when the process P1, who was working in the critical section, sets the value of S from 0 to 1. Then only their while loop, other processes while loop will be broken and they will be able to go to the critical section. Therefore, we can very clearly say that the requirement of mutual exclusion is satisfied here. Now, what about progress? So, see, progress requirement says that only those processes who are willing to go to the critical section must take part in the decision-making process of who will enter the critical section next. Indirectly, we can say that if P1 wants to go to the critical section, P2 should not be allowed to take part in the decision-making process, whether P1 will go now or not. So if you see in this one, any process who has to go to the critical section has to execute this part, and no process is actually dependent on anyone to change the values for itself. So suppose if P1 wants to go to the critical section, it has to execute these statements. If P2 has to go to the critical section, P2 has to execute these statements. Similarly, all the processes who wants to go to the critical section has to execute these statements, and no process is actually dependent on any other process to change the values for itself. Clear? So therefore, we can say that here the progress requirement is also satisfied. Clear? Now, what about the last requirement, that is the bounded waiting? The bounded waiting, if you take a scenario in this one, suppose there are these many processes P1, P2, P3, P4, and P1 goes to the critical section. And while P1 was working in the critical section, P2 requests for going to the critical section, P3 also requests, P4 also requests. So P1 can again go to the critical section. So it can be given the chance to go to the critical section n number of times, irrespective of the requests made by other processes. So we can say that here the requirement of bounded waiting is not satisfied. P1 can go to the critical section n number of times without worrying about P2 or P3 or P4. There is no such foundation on any process on the number of times it can request, it can go to the critical section. Therefore, bounded waiting here is not satisfied. Therefore, we can say the semaphore variable can be used to solve the critical section problem involving n number of processes, but it only satisfies two mandatory requirements of the critical section problem. The third requirement is not satisfied. So in the next videos, we'll see the other variants of semaphore variable where we can solve this problem of bounded waiting. So that is all in this one. Thank you so much.